So we're looking at linear approximation, and linear approximation is just a tool to help us solve problems like this. Find an approximation for 1 over square root 100.5. And linear approximation, we can use differentiation to help us with these types of problems. And I'll explain the concept to start with. I've got a graph here. This black line is my original curve, and if I draw a tangent line at point X, that's the red line, the tangent line. So we all know that tangent lines and differentiation are related, and what we're saying here in this rule is that if we find the value at fx, so this would be this value at fx, and we add on this approximate change, so this will be called approximate change. If we add the approximate change to the original fx, so our approximate change is actually this distance here. This is h times the derivative of fx. So if we add this distance to this distance, we get an approximation. And that approximation will be the approximation we'll get for this type of question. So we can use this rule to find an approximation. Our approximation will be this point on the tangent line. So let's have a go at this example and we'll see how it works. We have a question. Let's find the approximation of 1 over square root 100.5. What I'm going to start with, first of all, I'm going to change this into a function, and my function is going to be fx equals 1 over square root x. So in this case, x would be 100.5. But in my approximation equation or formula, this one here, we've got x plus h. This h is a small value. H is just the difference between x and x plus h. It's going to be a small value. If we go with a big value of h, say out here, you can see the approximation and the actual value would be quite big. So that's why we need to limit h to a small value. So what I'm going to do, I'm going to rewrite this equation, but this time I'm going to split up 100.5 into a big value, x. So instead of x, I'll write 100, and a small value, 0.5. That would be the h, the small change. The reason why I chose 100 is because we know what square root 100 is. So probably that's what you need to look at when you do these problems, is look at what you might know, and there should always be like a small difference that you can call h. The rest of the equation I'll just rewrite. So approximately this is equal to h, which is equal to 0.5, times the derivative of fx at 100 plus the original value at 100 of y. Okay, to work this out, what we need to find the derivative of fx and substitute 100 in. So we need to find the derivative of this. Let's do this over here. We've got fx equals 1 on square root x. Rewrite that in exponent form. That's x to the negative a half. Find the derivative. So to find the derivative, bring the minus a half down and take 1 away from the exponent, minus 3 on 2. Let's just rewrite that. We've got minus a half, x to the minus 3 on 2. So 1 over x cubed square root. Okay, so that's the derivative. We need to put 100 into there. Put 100 into here. So what we've got is 0.5 times minus 1 times 1 over 2 square root 100 cubed. Okay, plus f100. Okay, what's 100, square root 100 cubed? Well, square root of 100 is 10, and 10 cubed is 1,000. So all of that is equal to 1,000. So we've got approximately 0.5 times minus 2 times 1,000, minus 2,000 plus f100. Approximately minus 0.5 on 2,000 plus, let's work out f100. So we're just substituting 100 back into here. Okay, square root of 100 is 10, so that's going to be 1 over 10. 1 over 10. I want to get rid of this, a bit of a mix of decimals and fractions. I'll just multiply the top and the bottom by 2. So the top will become 1 minus 1, and the bottom becomes 4,000. Over here I want to make the same denominator, 4,000 as well. So that means I'll have to multiply it by 400. So what I've got, 400 minus 1, 399 over 4,000. So this is the approximate for this expression, 399 over 4,000. That would be this value. The actual value would be very close to that. Just notice here that because the tangent line runs underneath the original equation, the approximate value here would be less than the actual. This is the actual value. So if you typed it in the calculator, your actual value would be either bigger or smaller. In this case, the actual value is bigger. If we had another example, and I'll just draw it up here, if we had another example where, say, the line is curved this way and we did a tangent line, you can see that my approximate would be greater than my actual value. So depending on the shape of the curve, the original graph, your approximation might be larger or smaller. Just to summarise, that's the rule for linear approximation. This is the approximate change. So the approximate change was minus 1 over 4,000. That's the approximate change. That's the original fx value. Okay, good luck.